VDA Field Failure Analysis and Audit Standard from URGS International Certification and Inspection Private Limited. Hello everyone and welcome to URGS International Certification and Inspection Private Limited, our YouTube channel. Today we are going to discuss an important topic for the automotive industry, VDA Field Failure Analysis and Audit Standard. In the automotive sector, quality is not only about producing a component correctly at the manufacturing plant. The real test of quality begins when that component reaches the customer and operates in actual field conditions. A component may pass inspection, testing, and final quality checks at the manufacturing facility, but after being installed in a vehicle, it may experience a failure. This can result in customer complaints, warranty claims, vehicle downtime, production disruption, additional costs, and most importantly, damage to the reputation of the supplier and automotive manufacturer. So, how can organizations systematically investigate field failures? How can they verify the real root cause instead of simply correcting the immediate symptoms? This is our question. How can they establish effective corrective and preventive actions? And how can organizations audit their field failure analysis process to ensure that failures are being properly investigated and permanently eliminated? This is where VDA-based field failure analysis and auditing approaches become highly valuable. In this video, we will explain the concept of field failure analysis, the importance of VDA methodologies, the typical investigation process, root cause analysis, corrective actions, audit requirements, common mistakes, and finally, how URGS International Certification and Inspection Private Limited can support organizations worldwide through training, consultancy, auditing, and technical assistance. So let us begin. First, what is field failure analysis? Field failure analysis is a systematic process used to investigate a product or component failure that occurs after the product has been delivered to the customer or placed into service. In simple terms, the question is, why did the product fail in real-world operation? But professional field failure analysis goes much deeper than simply identifying the failed component. For example, suppose an automotive component develops a crack after several months of vehicle operation. A basic investigation may include the component cracked, but this is not the root cause. The organization needs to determine where did the crack initiate, what type of crack is it, was the material correct, was the heat treatment correct, was there a manufacturing defect, was the component overloaded, was there an incorrect assembly condition, was there corrosion, was the design adequate, was the component subjected to abnormal operating conditions, was the failure caused by the supplier, manufacturing process, assembly process, vehicle application, or customer usage? These questions demonstrate why field failure analysis requires a structured methodology. The objective is not simply to replace the failed part. The objective is to understand why the failure occurred and how recurrence can be prevented. Now second, why field failure analysis is important in automotive industry. The automotive industry operates with extremely high expectations for reliability and customer satisfaction. A single component failure can have consequences far beyond the cost of one replacement part. Consider a supplier producing thousands or even millions of components. If a failure mechanism is not identified correctly, the same problem may affect a large population of vehicles. This can result in warranty claims, customer complaints, sorting and containment activities, production stoppages, recall campaigns, additional inspection costs, supplier development activities, loss of business, and reputational damage. Therefore, field failure analysis is an essential part of the automotive quality management system. A strong field failure process should connect several functions. These may include quality, engineering, manufacturing, production, supplier quality, research and development, testing laboratories, metallurgy, materials engineering, design engineering, customer quality, warranty, and management. Field failure analysis should therefore not be considered only a quality department activity. It is a cross-functional technical investigation. Now, next is understanding the VDA approach. Third, VDA or the Verband der Automobile Industry. This is the full form of VDA. I again repeat it. Verband der Automobile Industry. VDA has developed numerous quality-related publications and methodologies that are widely used within the automotive supply chain. VDA methodologies emphasize structured processes, evidence-based analysis, and systematic improvement. When organizations use a VDA-based approach for field failures, the investigation should be controlled, documented, and technically justified. One important principle is do not jump to conclusions. For example, if a component fails because of fracture, the investigation should not immediately conclude that the material is defective. The investigation must gather evidence. This could include failed components, return parts, production records, inspection reports, material certificates, heat treatment certificates, heat treatment records, process parameters, machine settings, dimensional inspection results, testing results, assembly records, vehicle operating information, environmental conditions, previous complaints, and historical failure data. The objective is to establish a clear relationship between the evidence and the failure mechanism. This makes the analysis more reliable and auditable. The next is typical field failure analysis process. Fourth. Now let's discuss a typical field failure analysis process. Step 1. Failure identification. The first step is to clearly define the failure. What failed? Where did it fail? When did it fail? How many failures have been reported? Under what operating conditions? What was the service life? And what symptoms were observed? The failure description should be factual. For example, crack observed on the component after 35,000 kilometers. This is better than simply writing component quality problem. Now step 2. Failure collection and containment. The failed component should be properly identified, preserved, and controlled. Organizations should avoid or altering the evidence before analysis. Relevant parts may include the failed component, a comparable good component, components from the same production batch, components from different batches, and where appropriate, components from the customer or vehicle population. Containment may also be necessary to prevent additional failures. This could involve stock inspection, production containment, shipment control, additional testing, supplier notification, or temporary process controls. Now step 3. Visual examination. What is this? This is the next stage. The next stage is visual examination. Engineers inspect the component for cracks, fractures, wear, deformation, corrosion, discoloration, surface damage, improper assembly marks, manufacturing defects, and other abnormalities. Photographs should be taken and properly documented. The location and orientation of the failure are extremely important. For example, the location of a fracture can provide clues about the direction of loading. Now step 4. Dimensional and geometrical examination. The component should then be checked against drawing and specification requirements. Measurements may include diameter, thickness, length, flatness, concentricity, runout, surface profile, thread dimensions, geometrical tolerances, and other critical characteristics. Sometimes a failure may be related to a dimensional condition that was not properly controlled. Now step 5. Material and metallurgical analysis. For metallic components, material analysis can be extremely important. Testing may include chemical composition, hardness, microstructure, grain size, inclusion analysis, decarburization examination, heat treatment verification, fractography, and other metallurgical investigations. For example, if a hardened steel component fails prematurely, engineers may need to determine whether the hardness and microstructure are consistent with the required specification. Now step 6, fracture and failure mechanism analysis. One of the most important steps in determining the actual failure mechanism. Possible mechanisms include fatigue failure, ductile failure, brittle fracture, fatigue fracture, ductile fracture, brittle fracture, stress corrosion cracking, hydrogen related failure, wear, overload, thermal damage, corrosion, manufacturing defects, or a combination of several mechanisms. This is where technical expertise becomes extremely important. The investigation should distinguish between the failure mode and the root cause. For example, failure mode, fatigue failure, but the root cause could be incorrect heat treatment, sharp geometric transition, surface defect, improper machining, excessive stress concentration, or abnormal operating load. Now, fifth, root cause analysis. Once the failure mechanism is established, the next question is why did it happen? This is where root cause analysis becomes critical. Organizations may use tools such as 5 why analysis, Fishbone or Ishikawa diagram, fault tree analysis, cause and effect analysis, 8D methodology, failure mode and effective analysis, and other structured problem solving techniques. Let's take a simple example. Suppose an automotive shaft has fractured. Why did the shaft fracture? Because the fatigue crack propagated through the shaft. Why did the fatigue crack initiate? Because of a stress concentration at a particular location. Why was the stress concentration excessive? Because the component geometry or machining condition created an unfavorable transition. Why was that condition not detected? Because the inspection or process control method was inadequate. Now we are moving from the symptom toward a systematic cause. This is the fundamental purpose of root cause analysis. A good corrective action should address the actual cause, not just the visible symptom. Now, sixth, corrective and preventive actions. After identifying the root cause, the organization must implement corrective action. Corrective action should be specific, effective, verifiable, documented, and sustainable. For example, simply replacing failed components may be considered containment rather than a permanent corrective action. Permanent corrective action could involve design modification, process modification, tooling improvement, heat treatment optimization, improved inspection, supplier process control, operator training, specification clarification, error proofing, additional testing, or improved process monitoring. The effectiveness of the corrective action must also be verified. This is an important point. An organization should not simply state corrective action implemented. Instead, it should ask, did the corrective action actually eliminate the failure? Evidence may include subsequent production results, testing, field monitoring, audit results, warranty data, process capability, or a defined period without recurrence. Now, next is importance of 8D in field failure analysis. Another important tool frequently used in automotive problem solving is the 8D methodology. 8D provides a structured framework for responding to customer complaints and quality problems. It generally involves team formation, problem description, containment, root cause identification, corrective action, implementation, effectiveness verification, and prevention of recurrence. However, 8D should not become merely a paperwork exercise. A professional 8D should be supported by evidence. For example, test reports, photographs, measurement data, process records, material certificates, laboratory analysis, root cause evidence, and verification results. The quality of the 8D depends heavily on the quality of the investigation behind it. This is why field failure analysis and structured problem solving should work together. Now next is, what does auditing mean in field failure analysis? Now let's discuss the audit aspect. An audit is not simply checking whether documents exist. A professional audit should evaluate whether the organization's field failure process is actually effective. An auditor may ask, is there a defined field failure procedure? Are customer complaints properly recorded? Is the failed component traceable? Is containment implemented promptly? Is the investigation performed by competent personnel? Are laboratory and technical investigations properly documented? Is the root cause supported by objective evidence? Are corrective actions linked to identified causes? Is effectiveness verified? Are lessons learned communicated? Are similar products reviewed for potential recurrence? And are management and relevant functions involved? These questions help determine the maturity of the organization's failure analysis system. Now next is common mistakes in field failure analysis. Ninth, let's look at some common mistakes. Mistake number 1, treating the symptom as the root cause. Replacing the failed component does not necessarily eliminate the cause. Mistake number 2, insufficient evidence. Conclusions should be based on technical evidence rather than assumptions. Mistake number 3, destroying evidence. Improper handling of written component can make investigation difficult. Mistake number 4, poor documentation. Photographs, measurements, test results, and investigation records should be properly maintained. Mistake number 5, weak corrective action. Corrective action should address the actual root cause. Mistake number 6, no effectiveness verification. The organization should confirm that the problem has not returned. Mistake number 7, failure to share lessons learned. If one product experiences a failure, similar products or processes should also be evaluated where applicable. Now, how URGS International Certification and Inspection Private Limited can support. Now, let's discuss how URGS International can support automotive organizations in this area. URGS can provide professional support covering training, consultancy, auditing, inspection, and technical quality services. First, professional training. URGS can conduct training programs covering VDA Field Failure Analysis and audit concepts, failure investigation methodology, root cause analysis, 8D problem solving, automotive quality tools, corrective and preventive action, audit methodology, and practical case study based learning. Training can be customized according to the organization's industry, products, and requirements. Second, consultancy support. URGS can support organizations in developing or improving their field failure management processes. This may include procedure development, complaint handling systems, failure analysis workflows, root cause analysis methodology, corrective action systems, documentation formats, and audit checklists. Third, internal audits and process assessments. URGS can support organizations through structured assessments of their field failure and quality management processes. The objective is to identify gaps, risks, weaknesses, process inconsistencies, documentation issues, and opportunities for improvement. Fourth, technical inspection and failure analysis support. Where required, URGS can coordinate or support technical investigations involving visual inspection, dimensional inspection, NDT, material testing, metallography, hardness testing, chemical analysis, failure investigation, and laboratory testing through appropriate technical facilities. Fifth, automotive quality support. URGS can also support organizations in related automotive quality areas including IATF 16949 awareness and implementation support, VDA related training, process auditing, supplier quality development, 8D problem solving, core tools awareness, internal auditing, and quality system improvement. Now, why choose a structured approach? 11th, the key message is simple. A field failure should not be treated merely as a customer complaint. It should be treated as an opportunity to identify weaknesses, eliminate root causes, and prevent recurrence. A structured VDA-based approach can help organizations improve the discipline and effectiveness of their field failure investigation process. The ultimate objective is not only to solve today's failure, it is to prevent tomorrow's failure. And this requires competent people, reliable data, technical analysis, structured problem solving, effective corrective action, verification, and continuous improvement. Now, at last closing. If your organization is involved in automotive manufacturing, component production, supplier quality, engineering, quality assurance, inspection or customer complaint management, understanding VDA field failure analysis, and audit practices can provide significant value. At URGS International Certification and Inspection Private Limited, we support organizations with professional training, consultancy, inspection, auditing, and automotive quality solutions. For training, consultancy, or technical support related to VDA field failure analysis and audit standard, automotive quality management, supplier audits, and related quality improvement services, please contact URGS. Our email ID is info@urgsiso.com. Our mobile/WhatsApp number is +91 73 59 45 8455. Thank you for watching this video. If you found this information useful, please like the video, share it with your automotive quality and engineering colleagues, subscribe to the URGS channel and follow us more for videos on automotive quality, ISO standards, VDA, auditing, inspection, certification and professional training. URGS International Certification and Inspection Private Limited, supporting organizations in quality, compliance, inspection, certification and continuous improvement. Thank you, and we look forward to supporting your organization.